Urban flooding is a growing problem worldwide. Heavy rainfall and poor drainage can lead to a dangerous situation. Hi everyone! In today's video, we will walk you through a simple yet powerful C++ program that evaluates flood risk levels based on a rainfall and drainage data. This kind of tool is more than just a coding practice. It supports urban planning and infrastructure development. It helps create flood risk maps, strengthen emergency preparedness, and serve as an educational simulation in civil and environmental engineering courses. Let's start by understanding the problem this program solves. During heavy rains, drainage system may become overwhelmed. Engineers need a quick way to estimate how risky flooding might be in different situations. That's where our code comes in. It uses rainfall intensity and drainage capacity to determine the level of flood risk.
Now, let's break down the code. First, we include the required libraries. iStream lets us use cin and cout for input and output. String helps us store text like high risk or low risk. This is our custom function. It takes rainfall intensity in millimeter per hour and drainage capacity in liters per second as inputs.
Inside this function, we calculate storm water demand using this formula. Here, 0.08 is the land area in hectares. 2.78 is a conversion factor. Together, they help convert rainfall into liters per second. For example, if rainfall is 100 millimeter per hour, then storm water demand equals 100 times 2.78 times 0.08 equals 22.24 liters per second. Next, the program compares drainage capacity with fractions of the stormwater demand. As you can see, we used if-else in our code since we have a lot of conditions. So, if drainage handles less than 50%, it's severe risk. Between 50% and 75% is high risk. Between 75% and 90% is moderate risk. And over 90% is low risk.
The main function asks the user to input rainfall and drainage data. Suppose we enter 100 mm per hour for rainfall and 20 liters per second for drainage.
Now, we compute.
So for the given formula, the stormwater demand is equals to 100 times 2.78 times 0.08, which is 22.24 liters per second. Now, the thresholds are, for 50%, we have 11.12 liter per second. For 75%, we have 16.68 liters per second. For 90%, we have 20.016 liter per second. Our input is 20 liter per second. That's more than 75%, but just under 90%. So the program correctly returns moderate risk.
This code is a great tool for urban planners designing sustainable drainage, disaster response teams preparing for heavy rains, researchers creating flood hazard maps, and students learning hydrology and stormwater management.
It's simple, but it connects directly to how civil engineers work in the real world. Thanks for watching!